All right, guys. So we're gonna look at boundary condition. So this morning, where we left off, we said that light is an example of light waves is an example of electromagnetic wave. So we all did basic physics. So we are familiar with Snell's law. Sin I over sin R equal mu. So let us look at electromagnetic wave in general, going from one medium to the next. So when an electric field passes from one medium to the other medium, it is important to study the condition at the boundary between the two mediums. The conditions existing at the boundary of the two medium when field passes from one medium to the other are called boundary conditions. Depending on the nature of the medium, there are two situations of the boundary condition. Boundary, one boundary between conductor and free space, and two boundary between two dielectrics with different properties. So first, the free space is nothing but a dielectric. Hence, first case is nothing but the boundary between conductor and dielectric. So again, we start with Maxwell equation. The integral of E dot dl equals 0. And the integral of D dot ds is Q. Now I want you to imagine for me an electric field impinging upon a boundary. So here you have a boundary. This is medium 1. This is medium 2. And you have an electric field. The first thing that's going to be instructional is that this field, the vector, so you can resolve it into a normal component and a tangential component. So this is your normal component This is your tangential component. So your vector field, your E, is equal to E normal plus E tangential. With me so far? I'm not hear nobody yet to that.
Yes, sir. So far.
Okay.
Wait, sir, can I go back up a bit there? You fix there. So basically, the line that's in the center there would be our E.
This is your E. So this is your vector. So two vector addition. So you resolve this vector, which is your E.
Thank you, sir.
Into the normal and the tangential. All right? Now, so consider a boundary between conductor and free space. The conductor is ideal having infinite conductivity, such conductors are copper, silver, etc., etc. The field intensity inside the conductor is 0, and the flux density inside the conductor is 0. No charge can exist within a conductor, which we said this morning, so we were a little previous. The charge appears on the surface in the form of surface charge density. The charge density within the conductor is 0. Thus, E, D, and rho V within the conductor are 0, while rho S while rho S is the surface charge density on the surface of the conductor. So to determine the boundary condition, let us use the closed part of the Gaussian surface. Consider the conductor free space boundary as shown below. So this side is your conductor. This is free space. All right. Take a good look.
Wait, sir, so all of that is the conductor and free space, or is that each of those are different representations?
Yeah, this is this side. This is your boundary. This is free space over this side. This is your conductor on this side. Now,
So are they on ground?
huh?
Or is a Gaussian surface? I was asking if it's on ground, but I see that it says it's a Gaussian surface.
Yeah. So
So the
let
conductor.
go ahead.
Okay, sir.
No, man, go ahead. Let E at the boundary, electric field at the boundary. Let E be the electric field intensity in the direction N. I wonder if there's another figure. I think they mean that same figure. Okay. So E is the electric field. Okay? Making some angle at the boundary. So E is resolving a tangential component and a normal component. So we already know that the integral of E dot dl is 0. So E dot dl over the closed part is 0. So this is we're gonna choose a closed part here. So E dot dl over this closed part is 0. All right? So it's the integral A to B, B to C, C to D, D to E. That's your closed part. So for convenience, we choose the closed part that this and this are tangential to the closed part, to the surface, while this and this are normal.
Wait, second, go pause the answer. Just on the formula. So that's for like a three-dimensional shape, just to clarify. Or we just or perceiving it like the surface area. Sir?
Yeah, I'm not sure what you're asking.
As in this formula that on the screen right now, sir.
Mhm.
This is for like the closed like the charge on the surface, sir. The surface
No.
of the
The integral of the E dot dl around the closed part is 0.
all right.
So we choose this closed part. We go
Oh, A to B, B to C, C to D, then E to A.
right? And we choose a closed part that this is for the most part parallel to this and this.
Oh,
and this is at right angle to this.
Gotcha, sir.
So,
And they basically cancel each other out, you know.
hold on. If E dot dl then would be E from A to B, E dot dl from B to C, C to D. That brings you around the closed part. That's your dl.
Yes, sir. Yes, sir.
So the rectangle is an elementary rectangle with elementary height delta H and elementary width delta W. This is your delta W, your delta H. So the rectangle is placed in such a way that half of it is in the conductor and the remaining half is in free space. Thus, delta H over 2 is in the conductor and delta H over 2 is in free space.
That down you asked you earlier, sir. If the conductor and go right through halfway, but that sum it up.
Okay.
Cool.
Now, the portion C to D is in the conductor where E equals 0. Come, let us go there now. So this is in the conductor. I remember we say what? E is 0. So if we know that that is 0, because we know that E is 0 because there are no charge in it, you can drop out that, right?
Yes, sir.
So now, we're gonna shrink this delta W, make it get smaller. So as we get it small, E over it can be assumed to assume constant. All right?
Just E over A, sir?
We are saying that we make this delta W small. So we bring A closer to B or vice versa. And they're almost touching. So if them get very, very close together, E, we can assume that E is the same over that length, right?
Yes, sir, fair enough.
Fair enough?
Yes, sir.
So we can take out the E. Right? So E dot dl become E. We take it out because it's a constant over A to B. Okay? So then, but delta W is a long the tangential direction to the boundary, in which direction E equal E tangential. So E now becomes E tangential. Right? So B to C is parallel to the normal component. So we have E equal E normal along that direction. Right? So in a similar way, over the small height, delta H, E normal can be assumed to be constant and can be taken out of the integral. Same way. Same thing we do with the E tangential. But out of B to C, B to 2 is in free space, and 2 to C in the conductor, where E is 0. So delta L now becomes this. This is 0. Follow that for me.
Repeat that, sir.
Just, I said, follow that for me. Follow what is on the screen and tell me if you have any questions.
Sir, 2 is not necessarily is it the number you integrate from B to 2, or is it just a location on the surface?
B is a point on the boundary, right, sir?
Yeah.
Sorry, two is also one of the points on the boundary.
Yeah, man, here it is. Yeah. From here to here.
Oh, that's free space.
Mhm. You okay with that now?
Still try to take it easy. Whoa, careful. Still try to understand it, sir.
Take your time, take your time.
So can you run over the delta W from the line that go down, sir, please? One more time. Then.
Run over delta what?
From which way I have 5. Number
5.
5, yeah. From this side I go down, sir. Them 3 line there, please.
This from here.
Yes, sir.
Picture it in your mind. This is it. This is normal, and this is normal to the surface. Huh?
All right, yes, sir.
So we say now BC is parallel to the normal component. So we have E equal E normal along this direction. Let En be that. Over the small height, delta H, E normal can be assumed constant and can be taken out of this. So we just take it out. Because we say E normal, if we shrink it, E normal is constant. So we end up with this. All right? And delta L is delta H over 2 outside of the conductor, because since E is 0 in the conductor, we can leave that out. So we're left with this. Right? So we end up with this. Similarly, on the other side, we end up with the same thing. This now becomes negative because we're going around the closed spot, so we're going in a different direction. So here, when we sum it all up, it becomes 0. So E tangential is equal to 0. So we said the tangential component of the electric field is 0. Key point. E at the boundary between conductor and free space is always in the direction perpendicular to the boundary. So E tangential is 0. Right? So D is epsilon naught E. So D tangential is also 0. So now go back to your figure here.
Sir, we have less than a minute, sir.
Yeah. In that minute, take a mental picture of this.
So before we time out, sir, can you remember what the D stands for, sir?
Anyone?
The electric field, so electric field strength. Said E, right?
Yeah, D, no, D, D,
E.
D, as in the,
Electric
Oh, electric flux density. Is it the gas?
Mm. So let us now look at the so we have that pillbox, right? So to find the normal component of the select a closed Gaussian surface in the form of a right circular signal as shown. Its height is delta H and is placed in such a way that delta H over 2 is in the conductor and the remaining delta H over 2 is in free space. Its axis is in the normal direction to the surface. We got that, right? Yeah, Mr. Thompson.
Oh, sir, wanted to ask if for the E10, is it a case where it's like equilibrium equation? So you have to sum up everything and equal to 0 and you can solve for any missing one or something.
Yeah, pretty much.
Oh, all right.
All right. So back to that pillbox. We know that the integral over the closed loop of d dot ds is q. Right? So for that pillbox, we have the top, we have the bottom, and we have the side going around, right? So the integral over that closed surface is this. That equal q. The bottom is in the conductor, we know that's 0. The top surface is in free space. Thus, we are interested in the boundary condition. Hence, top surface can be shifted at the boundary as shown. So we pull down, we shrink the pillbox, so delta H go to 0. The side is 2 pi r h, which is delta H, where r is the radius of the cylinder. No problem with that, right? But we have delta H going to 0. This area reduced to 0 and corresponding integral is 0. While only component of the present is the normal component having magnitude d normal. The top surface is very small, over which d normal can be assumed constant, and hence we can take it out of the integral. So we get this. So all we are left with is this. Now digest that and tell me if you understand that. Take your time.
So I'm going to substitute Q equal the rho S and delta S.
Substitute what? Yeah.
And then factor the delta S
Right.
by delta S.
Mhm. We good?
For the most part, so not get your right, but yeah.
Okay. Now, um, so there is something I want to add to all of this now. So at the boundary, E tangential 1 in region 1 is the same thing as E tangential in region 2. They didn't spell it out here. Similarly, at the boundary, D normal 1 is equal to D normal 2. All right. So we're gonna go now to we go to chapter 2 of Wentworth. Okay. So here, so here is a problem now. Can you read this? I want you to see the solution. So I have to go back up here. So here's the problem. For y less than 0, ER1 is that, E1 is that. And y equals 0, at y equals 0, rho s is that. If ER2 is that, for y greater than 0, find E2. Let me see you try that.
So what's that second symbol, sir? After y less than 0?
Well, y less than 0, ER1, epsilon R1.
Okay.
So I'm giving you 15 minutes to do that. Oh, God, I'm tired. It's Friday. Anything yet?
Boy, sir, my last bat, sir. I don't understand what for with this, sir. Because, like, I try to use the formula, sir, but I not get, like, what may I expect to get. I get one value. And not to make sense.
Okay.
Sir, the only thing we'll be doing is that just write the normal, the tangent and the electric field, the drawing for it, and label it. You know how to proceed from there.
Me just drop the values that we have so far, sir, in the formula for E. But that, like I said, I just give it one value and I already give it the vector. So now I wonder. I can't lost me now.
We have that, right? Z, Y, X, right? So then, it says for Y less than 0 and Y greater than 0. So you know, it's in the XZ plane, right? Because Y less than 0 is this way, Y greater than 0 is this. So the thing is in this plane, right?
Yeah, man, sir. Yeah,
Yes, sir.
that's
All
an
right.
easy.
So it's a E1, ER1, or Y less than 0 is 4. So ER1 over this side, or epsilon R1, equal 4. And epsilon R2 over this way equal 2, right? No, 5. All right. So it tell you now that E1 that it says over here is 5AX. So 5AX,
3 and 3 that, sir.
3AX,
Yeah.
6 pi AY, so 6 pi AY, and 4AZ, 3AX, 6 pi AY, 4AZ. So you have to mark that, right?
Right, sir.
So you want that are E1.
Yeah, man, sir.
So now, just look at this.
The 6 pi, sir.
No, look at E1, right? So remember it's in the XZ plane. So
can integrate the Y, sir.
So what is normal to the plane?
The Y, sir.
So 6 pi AY is normal. So write that down. E normal 1 is 6 pi AY.
Okay.
You have that?
Yes,
Come
sir.
on, sir.
So what is E tangential 1?
Sir, it would be the rest of the 3x.
Yeah, the 3x plus the 4 AZ.
Yeah.
So you have E normal 1 and E tangential 1. All right?
Yes, sir.
So what's E tangential 2?
Same thing.
It's the same thing. So then, rest is easy. E1 is this. E normal 1 is this. E tangential 1 is this. So if we have E normal 1, this is E normal 2. No, this is D normal 2. Epsilon times E normal 1 is D normal 1. All right. Remember, D is E epsilon. No, D is epsilon E.
Oh, yeah. Yes, sir.
So you have
Yes, sir.
E normal 1. All right? By just doing this, you have E normal 1 and E tangential 1. So you have D normal 1.
But then one issue, sir, for the next step, sir, how them get E2 to be that value, sir, as in the Y value for that, sir.
Hold on.
Oh,
That would be, we follow it then. You have E normal 1 and you have E tangential 1. We see that, right?
yes, sir.
Yes, sir.
Come to see now. E tangential 2 is equal to E tangential 1. So it's the same thing. Right?
Oh, yes, sir. Oh, yes, sir.
So then go to D now. We have D E normal 1, so we can find D normal 1.
Yes, sir.
Right?
Yeah. And then from that, we'll find
D normal 2
normal
is
2.
equal to D normal 1.
Wait. D normal 2 is equal to D normal 1, sir? Oh. And then E normal 2.
So from we find D normal 2, we divide by epsilon to find E normal 2.
What's that, sir? 5 epsilon naught?
Yeah. ER,
And that's
E naught.
because, you said again, sir?
ER, just like this. ER2 E naught equal that. So you
Oh.
divide. So you find E normal 2. And E2 then would be E normal 2 plus E tangential 2.
Sir, you find D normal 1, D normal 2 again. Sir.
D normal, you find D normal 1.
Yes.
And D normal 1 equal D normal 2. And E tangential 1 equal E tangential 2. So you find D normal 1 here. If you do this, if you work this out, it'll give you this. So D normal 1 equal D normal 2.
Sir, for epsilon naught, you use E over D,
Epsilon naught.
D over E, sorry.
D over E.
Yeah, from think is if
Remember, you know, epsilon equal epsilon R, epsilon naught, where epsilon naught is the permittivity of free space, right? Which is 8.854 times 10 to the minus blah, 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 or 36 pi over something another. That's a constant. E naught is a constant. So ER is what's given here. ER2, epsilon R2 and epsilon R1. So D equal epsilon E, right? This is epsilon R1, epsilon naught, right? So here, if you multiply 4 times epsilon naught, you get 24 pi epsilon naught for D, because D equal E epsilon E.
So, two questions. Is it that E tan 1 is always going to be equal to E tan 2?
That's why we prove this when we come back and we're developing it. And we are shrink the thing and all that. So E tan 1 is always E tan 2.
Thank you, sir.
And D normal 1, when we shrink the pillbox, is equal to D normal 2.
Sure.
So what was that bit you said right there, sir? When what is
When we shrink the pillbox, when we were proving the thing,
yeah.
we prove that D normal 1 equal D normal 2.
Oh yeah. I remember that. Yeah, thanks, sir. And D normal 1 is equal to epsilon E normal 1.
Right.
So when I work out 24 pi epsilon naught, so I'm not getting the 0.92.
What you get?
I'm getting a value of 6.68. times 10 to the negative 10.
What you use for epsilon naught?
8.854
Oh.
times 10 to the negative 12.
Eh?
I use 8.854 times 10 to the negative 12.
.854 times 10 to the negative what?
12.
12, yeah. And you work this out and you get what?
6.68 times 10 to the negative 10.
So, sir, where does the surface density come in play? I will ignore that.
So far we have been doing that. Hold on a second. Okay. Okay. We have a surface density here, you see, which play a trick on us. So the normal, if you add now, the normal one, what you say you get again?
6.68 times 10 to the negative 10.
Add it to this and see what you get. No. Yeah. Here it is. What I did was ignore that. I ignored the surface density, but here you are. Here is it.
I got it.
Sure, the 0.25, that's it, right?
Mhm. All right. See if you can manage 63.
Rob's. Morning, everyone. Total family rule here. No.
Okay. So what you did with that one?
First things first, sir. You draw the diagram, representation. And since you know that we're doing it in the XY plane, you draw the normal to the XY plane, and then you draw E1. But then I wasn't sure how the angle come into play with the calculations from there on. Oh,
We use like Snell's law, it seems like. Oh, so.
See if that makes sense.
sir, ET1 as in E tangential one?
So this is E1, eh? And this is E2. So this is your Z. So you set him
Isn't
up.
that the normal, sir?
Hmm?
That's the normal, right, sir? That you was talking about.
This?
Yeah.
No, man, that's the entire
No,
E1.
as in that E1 is going into. That's the normal.
I don't get your question.
Oh, no. It's okay, sir. When it is, sir, it's just observation with me.
Oh. Any question? Take your time,
Sir,
take your time, take your time.
sir, is it that since they didn't state the charge density on the surface, we just assume it to be 0?
Yes,
Or-
it is right. Here it is.
Yeah. Because when I see it, then just assume it, sir. So I'm gonna say I wonder.
We're good, so we can see if we get in one more.
Sir, is it a given thing that field intensity over flux density give the tangent?
Say what?
Is it a given? I see them of the field intensity over the flux density. Is that a given thing?
Oh, yes, it is.
Under therefore,
So ER1 over D1 huh? Minus this.
yes, sir. Because I was wondering how they know that for the field intensity that you should use sine and not cos.
So they ask now. We have this, right? All right, this is your thing, right? So
Yep.
so first, let's follow the thing. E tangential 1. This is your line. So E tangential 1 is going to be this sine. It's going to give you this side, right?
Yes, sir.
It's going to be E1 sine theta 1. All right? And E tangential 2 is going to be E2 sine theta 2. All right? Which is going to be this. This is supposed to be 2. And if I fool me, this look like a 1, see me.
Yeah, no, it's supposed to be 2, sir.
But this is supposed to be 2. So this, you see what this equal this?
Yes, sir.
Okay. This. All right. So D normal 1 now is gonna be epsilon times E normal 1. E normal 1 is E1 cos this, which is this. So D normal 1 is gonna be epsilon times E normal 1. Right? You see this?
Yes, sir.
And then your E normal 1 equal E normal 2. So you equate these and you get this. And you do a little trigonometry, you get the theta 2. I don't know, boss. I'll give them one more. I'll do that for next week. I'll give them something.
One more like that, yes, sir.
Eh?
One more like that, sir.
When I try to find one which is our next coordinate system, but all right. There you go. A plane defined by that separate two dielectric. All right. Yeah. That one's supposed to be a piece of cake. All right, do that for next week. Come tired.
2 by 6 4.
Yeah.
Oh, bossy.
All right. Take down that. Let me see if I can find one next one too. With a different coordinate system. You have that done already?
Oh, wait, sir, wait, sir.
No, sir. Really.
Get that done. I promise them guys one class 4 o'clock now. I'm not even know if we can manage that. Get it?
Yeah, man, sir. Wait, well, I don't know if the others get it, sir. Sorry.
Yes, I have it, sir.
I'm gonna say I'm gonna find the next one. Well, this is not a boundary condition problem, but do this one. Do this one as well. Do them two if you homework. We talk nothing about no midterm yet. Next week.
A week after, yes, sir.
That me say.
So when you do 30, sir, look for grade them, sir.
Eh?
When you do 30.
No, a week after, man.
You never hear when sir say week after.
Well, I should have been about it. All right, go ahead.
So you can compare everything you taught thus far?
Yeah, man.
So I know, sir.
And like how you put it for week after, I go have one next week too. But especially in that book, Sadiko, if you, they have some nice examples of the boundary value problems. Even nicer than this.
Yes, sir. We know how to work out those examples are good.
You have a good for one of the questions, yes.
One.
About 25%.
And how much question I got there, sir? 4?
Me go see how me can give you this thing online, yeah?
There.
Yes, sir. That
But me not give you the final online, I promise you that.
we see, sir. We see.
I think you can bribe me.
Right, I ain't got
Oh,
those ones, sir.
sir, is there a way that we're supposed to contact you, like, if outside the class? I'm not aware of that.
You know, WhatsApp number, man. I have an email and whatever.
And the same check.
I'm tired, man. I gotta take a break. I'll see if I can teach them people at 4 o'clock.
Awesome.
All right, sir.
All right.
Sir.
Yeah.